Okay, so shall we start?
Okay, for sure. Hi, everybody. Welcome to this tutorial. It is my great pleasure to introduce Professor Bruno Ribeiro. Bruno is an assistant professor at Purdue. Associate professor at Purdue. Excuse me. He is also a visiting associate professor at Stanford University at the moment. His research spans various topics in machine learning, in particular invariant theory and learning from graphs. His research has been recognized by tons of awards, including the NASA Career Award, Amazon Research Award, and so many other research paper awards. With that, Bruno, thank you.
Thanks, Babak. I will start with a disclaimer. The idea for this tutorial came about when I was Babak has invited me here to talk about this amazing research that he's been doing and how it connects with the research I do. And then at some point I was explaining something. I said, well, I have lectures. I could just give a lecture on this. And then Babak decided to say, like, we talked about sending an email to other people to see if there was interest. And somehow it snowballed into a whole tutorial that's being advertised and has a bunch of people online. So why do I say this is because if you see typos, if you see the notation is not too consistent, it's because I was not expecting this to happen. But so I'm going to talk about building a G-invariant and G-equivariant neural networks in a specific way, and then I'll generalize a bit at the end. So these are neural networks that are invariant to transformations. And I'm going to explain this notation soon. We start with G-invariances, the notion that it should be the output of the neural network should be invariant to transformations of the input. And then I'll show how to use the same toolkit from invariances to talk about equivariances. If you want to better understand the methods and further reading, we have a paper on this. And also, if you want to understand what I'm talking about with respect to the power of the representation power of these functions, you should read Jaroszewski paper on that. With that out of the way, I will say that all the transformations in this tutorial will be automorphisms. So because all the transformations in a G-invariant neural networks are endomorphisms. So for instance, you're essentially taking an object in a space and then mapping it to the same space, right? That's what an endomorphism means. So you get this, say, image, and then it transforms, and it's still an image in the same space. So if the transformations are associated with a group, and we are going to see what that means, then there'll be automorphisms, because for groups, the transformation must have an inverse. So it must be able to invert the transformation. So we also restrict attention right now. Later we will generalize this to linear transformations. What is a linear transformation? Is that if I add two of the inputs, then the transformation is applied to them separately. You essentially add the transformations. And if you scale the input, then it's just scaling the transformation. So we have a papers explaining how to generalize this to nonlinear transformations. At the end of the lecture, I'll talk a little bit about this. But for now, we're going to use just linear transformations. And they cover a lot of interesting cases anyway. So now one thing that I would say is that earlier in the literature, folks were doing some kind of intermediate space representations of, but I would say just try to avoid that. Say transform an image into a point cloud and then back into an image, because if you do that, then sometimes the math doesn't quite work out. You should try to do that directly, the transformation directly on the space. So. So the transformations will be always on endomorphism, right? So we have, say, this image here is a 20 by 28 grayscale image. of a 4, then you vector. So what we are going to do, which is very important to understand, is that we are never transforming the original space, because this is a matrix, right? 28 by 28. We are going to always vectorize whatever the input is. And when we talk about graphs, this is also true for graphs. We're going to vectorize a graph. So we're going to vectorize the input and then apply the transformation. And the new vector will be the transformed input. And then you can have this operation of unvectorizing and then seeing the result. So I am going to usually show the input and the output. I'm not going to show you this vector because we are humans. We're not able to understand this is a 4, okay? But we always think that these are vectors. They are not matrices or tensors. The tensors are also vectorized. So, so what happens is that the input will be 28 by 28, but the vector is 784 dimensional vector. Okay, and the transformation is a transformation that takes the domain of 784 dimensions and map into a codomain of 784 dimensional. So let me, just avoid this type of intermediate transformations. You try always to go to the original space, vectorize, and go to the unvectorized, transform and then unvectorized. Okay, so let's talk first what's a G-invariant neuron. Okay, so this on the left is a standard neuron. What's a standard neuron is essentially this equation, right? So this scalar output, which is the neuron output, is going to be some non-polynomial function, which usually we call nonlinear function here, sigma, and then you have this inner product between some weights that you have to learn, and then your input, right, x, plus some bias. Okay, so that's what the neuron is this inner product plus a bias. And that's also true if x is, rather than being the input, is some other layer of your neural network. Okay, now what's the invariant neuron? The invariant neuron has basically the same math, is the same type of neuron, it's no different. The only difference is that you see here that the weight of my neuron was unrestricted in the 784 dimensional space, right? If my axis that has dimension 784, then I have 784 weights to learn. However, for the G-invariant neuron, I'm restricting this neuron into what we are going to call invariant subspace of the entire space, 784 dimensional space, right? So if your vector input has n dimensions, then it's going to be a subspace of Rn. Okay, and that having this vector as a subspace, this subspace is called invariant subspace because it has the property that if I transform x and I do the inner product, the output will be the same no matter which transformation of x I apply. So let's, before we look into the details of this invariant subspace, let's see how the invariance, how it affects invariance properties of the G-invariant neuron. So, the following image, for the following image is image x, we are going to compute this inner product with this weight vector, and we are going to also compute the inner product with a transformed input where I'm going to do a 90-degree rotation of my image, okay? And then note that this inner product acts as the vectorized input, right? So what I'm going to show you is essentially this. I'm going to show you the sum of the unvectorized, so you can see as an image, in a Hadamard product, right, element-wise product with the unvectorized. Sorry, the weight will show as an image, and the input will also show as an image. And you do element-wise product, and you sum everything. So that's essentially the inner product, right, of the vectors. And then you can later, when you look at the tutorial, you can download this auxiliary library that will help us do this. Okay, so here's the scary part. I'm going to run everything live. So let's see if this works. Okay, so I'm giving a rotation angle of 90, and I'm first showing. Oh, what's happening? Oh no, it takes a while. Wow, that was scary. Okay, so so I am showing this weight matrix is restricted to the invariant subspace. Okay, so I am doing inner product of this vector against this vector, and this is the output. Now I rotated my 90 degrees, and I'm doing this inner product with the same weight matrix, and you can see that the inner product is still the same. Okay, so the task then is how do we get to learn what the invariant subspace is? So that's what we are going to see in the first part of this tutorial. Okay, this is because this invariant subspace is built in a way that remain invariant under rotations. That means that the W weight matrix, if multiplied by the transformation, this is a matrix, as we'll see later, that rotates my image as a vector. It remains the same. Where have you seen this? Yes, we are going to connect this to eigenvector. So this invariant subspace is actually invariant subspace of an eigenvector or something that's related to this group. Okay, so let me show you. Let me show you this actual multiplication. Oh no. Yeah, as a yeah, this is free. It's open source. So sometimes it doesn't work as well. So this is my W, my weight vector, and this is the weight vector multiplied by the transformation multiplied by the weight vector. You can see that it doesn't change, right? It has the property we want. Okay. So the question then is, how do we construct this invariant subspace? So the first part of the tutorial will be about this. We are going to see that this invariant subspace W is the left eigenspace corresponding to eigenvalue 1 of the Reynolds operator of this transformation group. If none of this is clear, it's okay, because I'm going to explain this in details. In the previous example, the group is the rotation group that rotates an image by 0, 90, 180, and 270 degrees. And what I'm going to describe next is how to compute this. And then what I'm going to do now is I'm going to talk generally about groups, right? Okay, so not sure. Let's do it like this. Okay, so what we are saying, we're going to see what's a group, a billion or not, finite, infinite groups, general linear group. And then we're going to show how to construct the Reynolds operator and find a basis for it. And then how to find the eigenspace of this linear operator, general linear operator as a black box. We'll talk about invariant subspaces, and then I'll show step-by-step examples, finally going into G-equivariant networks. So let's then talk a bit about transformation groups. Oh, okay. Okay, so the definition of transformation group is a relationship between transformation groups and symmetries. If A and B are symmetric transformations of an object, then clearly composing both transformations will preserve the symmetry, right? If you say that something doesn't change as you rotate it, you can rotate it 90 degrees, 180, 270, and it's the same thing. So a transformation group consists of a set of transformations G and a binary composition operator, which is this, what we're going to call the action, defined between two elements of, no, this is just the composition defined between two elements of the group. So so a group is just a set of transformations, but it has to have the following four properties. For all transformations in your group, the composition of the transformation should also be in the group. That's very important. And that will restrict the types of transformations that we can deal with. It's also associative, meaning if you first apply B and C, and then apply A, is the same as applying A to B and then applying C. There exists an identity if one of the transformations leaves the object the same, exactly the same in the space, and this identity is unique in the group. And finally, which is an important property that unfortunately we have, which also further restricts the applications we can use this for, is that the transformation needs to have an inverse. So there is always an inverse, so that applying the transformation times it and applying its inverse will be the identity. Okay, and the inverse is unique for each transformation. So let's see an example here. Let's talk about 90-degree rotational symmetry, right? We have the identity. So here we have an image. Now we do a 90-degree rotation. There is another operator that's 180 and 270, right? The rotational symmetries of a square. Do this satisfy the group property? Is this a group? Identity? Yes? All the compositions of the possible operations, are they in the group? Yes? Right? And then if you look at the two other properties, they also satisfy it, right? So for instance, if you compose 180 with 270, you get 90, right? If there is an inverse for 180, which is itself an inverse of 90 is 270, right? So this is a group. So now that we have established this is a group, let's look at this. What about this? I can flip images, okay? So I have an image, identity, the horizontal flip and vertical flip. Are the group properties satisfied? Can I use this transformation? Can I be invariant to this transformation using the technique we are going to use? I see some no's. No? Why is that? Because a horizontal flip and a vertical flip is a 100-degree, 80-degree rotation, right? I'm applying horizontal and vertical, and now I cannot, there is no transformation here that if I apply to the input will give me this, right? So what do I need to do? I need to add 180 rotations here. Now let's add 180 rotations and check again, okay? Is this a group? Yes? Yes, and we can check that, right? So there are a few types of groups. One type, for instance, is commutative group or abelian group, or non-commutative. What is commutative is that the operations in the group, if you apply B first and then A, is the same as applying A first and then B. Okay? Is this an abelian group? Yes or no? Yes. Yes. This is an abelian group, right? Applying this rotation, if I apply another rotation, is the same as reversing the order, right? What about so this, for instance, the one that we created if we add vertical flips and diagonal flips to a group, right? Let's say this is the group that I created, right? It's a group because all the group properties are satisfied, but you can check yourself that this is not commutative. The order in which the operators are applied makes a difference. If you reverse the order, it's not gonna work. So rotations and flips are not. It's interesting if you add rotations and add flips, you have to add these other two transformations, the diagonal flips. Let's see an example. So we have here a horizontal flip and a 90-degree rotation. That gives me a diagonal 2 flip, which is different than the diagonal 1 flip, which would be obtained if we reverse the flip first and then 90 degrees, right? Flip first and then 90 degrees give you this. If you do 90 degrees, then flip, give you this. Okay? So they are different. There are other types of groups, finite or infinite. The number of elements may be infinite or finite. So I'll give you an example of infinite group, the Lie group. The Lie group, for instance, the rotations of points in Euclidean space would be around the center. Would be infinite group because you can rotate any angle you want, right? So you have an infinite number of transformations. Okay, we're going to talk about Lie groups later. Now a subgroup, if H is called a subgroup of group G, and then we have this notation here. If H is a subset of G and H is also a group. Let's go back to this example. For instance, you can see that the flip group, right, which is this 3, and the rotation group are subgroups of this group. And a very important group that we are going to spend a lot of the tutorial later in is a permutation group. So a permutation group is a group whose elements are permutations of a given set A, whose group operations are the composition of the permutations in G. So so given a set A permutation of A is this bijection, okay? And permutation group A is a set of permutations that can be formed under composition. So, for instance, if you permute the elements of a sequence, right, of n elements in a sequence, then you know how to compose, right? You permute them, and then you can apply another permutation, and that's the composition. So, for instance, if we have this input A, then we have this permutation. The permutation may take the first element, permutes with the second, and then the third remains the same, right? So you're just permuting things. So let me show you examples of the permutation groups. The symmetric group is a type of permutation group, is the group of all permutations on this set of elements. So if you have n elements, a group that talks about all possible permutations of this set is the symmetric group. There is an alternating group where the permutations are only allowed in alternating order. Cyclic group, that where the permutations are, they're just shifting the elements and putting the last one back in the first. And there is also the dihedral group, which is useful when you talk about rotation in solid. So let me show an application of the symmetric group. Think of a 3D point cloud, right? The order of the points, this is a car, and it's still a car, no matter how I have ordered the points inside my vector describing, or my matrix describing this car, right? So the point cloud, the order of the points in the doesn't matter. So then this is going to be whatever neural network operates on this should be invariant to the order of the points, the point cloud. Another example is an n-size graph sequence where you have n nodes and n square edges at most, right? And each edge can have a type. So later we'll see this is an adjacency tensor because the edges can have types and the nodes have features. But in any case, a graph can be seen as another object that is invariant under permutations of the nodes in this adjacency tensor. So the order in which I'm saying this node is 1, or this node is 2, this node is 3, it doesn't matter. It's the same graph, right? So then therefore this input here can be permuted in all these forms. And whatever my neural network does to this adjacency tensor, it should not matter, right? Okay, so let me, oh, what happened? Oh, what happened? How did you have? Oh, go back. Hey, hi. Okay, so so the group actions. So we'll see that what we want our final representation to be invariant or equivariant to the symmetric group. You can see, for instance, that the symmetric group, right, is just a vector telling me where the elements go, but it doesn't have an understanding of how to apply the permutation onto the object. For instance, here we have 3 dimensions on this tensor, right? If I say I want to apply the permutation group over this tensor, where am I applying? Am I applying the first dimension, the second dimension, the third dimension, and these 2 dimensions together, all 3 dimensions together? It doesn't specify how you're going to apply. So we need a new, another object to describe how we, looking at the permutation group, how things are, the elements are permuted, how we are going to apply to the original object, okay? And that is the role of the group action. So essentially what I'm going to do from now on is I am going to write, so if pi is a permutation in the permutation group, I'm going to write pi applied to x as I am going to permute in general for graphs. I'm going to jointly permute these 2 dimensions here, okay? According to the permutation that I got, because the permutation is just a vector, 1, 4, 5, 1, 1, 3, 2, which means that the second element goes to third, and the third element goes to the second. So let's describe this formally. Let's describe group representation formally, okay? And now I'm going to introduce a special type of group, which is the generalized linear group. So a linear finite dimensional group representation, let's call this rho, it takes an element of the group and then produces a matrix, okay? So the matrix is going to be a M by M matrix on R. It will associate an element of the group to a matrix transformation, okay? It's an invertible matrix, so all these matrices here need an inverse because we are talking about groups. Groups have inverses. So this representation satisfies the following. If you give the identity element in the group, the representation of the identity element is what we call the identity matrix, okay? And if I give you 2 elements in the group, G1 and G2, the representation of the composition of G1, G2 is the composition of the representation. So if I'm trying to find what's the transformation of my tensor, for instance, that will permute the tensor, okay? I am going to say, well, these are the permutations I want. I apply first this one and then this one. And this, as we know, since it's a group, it's an element in the group, right? So this is a representation of an element in the group. But it's the same as the applying first G2, the representation of G2, meaning I get the tensor and I permute it first, and then I apply the permutation of G1. I get the result and then apply another permutation, okay? So this will be essentially permutation matrices for a permutation group. The representation only has these 2 properties, and with these 2 properties, we can prove that any inverse in the group will be the inverse of this matrix. Okay, so this matrix all must be full rank because they need to have inverses. So the representation specifies how objects transform under the group, and can be considered a specification of the type of an object. So why is this important? This is very, very important. When we talk about equivariant networks, it's going to be strange because we are going to apply a permutation, or we're going to apply a transformation over the original object, they rotate it. And then what we want is the neural embeddings from that object should also be rotated. But since the embedding has a different space as the input, right? Input is say an image, and then the embedding could be just two neurons. You need to define what it means to rotate on the two-dimensional space of the embedding. And we are going to use this concept of representations, because for the input, the representation is different than for the output. Okay, it will be more clear when I get there. So, so let me give you an example for a set representation. So if pi is an element of the permutation group, which is essentially a vector of numbers of some permutation of the sequence 1 to n, right? We define rho pi as the linear group representation that will permute the 3D points in this space. So for instance, here we have a point cloud with n points in 3-dimensional space. And this row here will permute the points, the rows of this matrix according to pi. Okay, so it's going to be a matrix. We are going to vectorize this and apply this matrix to this vector. If none of this is clear, you can stop me. It's good to have some interactions if needed. So for instance, when I get this input, right, this point cloud, I'm going to vectorize it, and I'm going to pass through this. I'm going to multiply by this matrix, which is the representation of this permutation, to get a new vectorized x prime, and then I can unvectorize to get back a point cloud. Okay, so for graph representations, it's the same thing. Theoretically, you for instance, look at the adjacency matrix here of a graph with n nodes, and then there is a permutation matrix that is applied to a vectorized version of this adjacency matrix. Okay, so the permutations here are defined over vectorized versions of the input. It's always like this. So one thing that I want to say is that this sounds a bit counterintuitive, right? Because vectorizing a matrix sounds a little strange. But I'll say this, the math working on this space is infinitely simpler than the math working on things that you usually find when you describe permutation matrices of an adjacency matrix in a graph. This, very difficult to do math on. This is really simple. So my recommendation doing any math on graphs, always do this, a lot easier. And we're going to see that whatever, all the tools that we're going to describe, I'm going to describe today, and I'm mostly talking about images today, will be directly applicable to graphs if you do this. So let's show an example of vectorized. Let's look at this tensor that represents an RGB image m by m pixels, okay? This cute dog here, and I'm going to vectorize the dog. Now the vectorization is just a bijective mapping, okay? And you can do whatever you want. You can stack them, the channels first, or you can interleave the channels in the pix, whatever you want. Just remember what this transformation is when you want to reverse it. But once we vectorize, we forget that is whatever a tensor, we always work with the vector. So, okay, so I think that's clear. So an important group is the general linear group that I mentioned before. And this will be a group of all n by n matrices, all square matrices that are invertible. Okay, so all possible square matrices that are invertible, we form this group, the generalized linear group. And the operation of the group will be defined as a matrix product. So let's see if it satisfies a property of a group. If you have two invertible matrices, A and B, is the product invertible? Yes, right? You can just apply B inverse, A inverse, and you get identity. So you have an inverse. Okay, so it's associative. Yes, right, matrix projects are associative. Does it have identity? We know very well the identity. Is it invertible? Yeah, it has to be invertible. You see, because not having an invertible matrix doesn't make it, it's not a group then, because you don't have inverse for the operation, the transformation. Interestingly, in general, it's non-abelian, meaning, as you know, applying, multiplying AB is different than BA, right? We know that. It's also an infinite group. It's an example of an infinite group. So let's talk a bit more about why generalized linear group is very interesting. So for every matrix A is associated with a bijective linear mapping, okay? So it maps vectors in Rn to Rn bijectively. So that the notion of a transformation here of X is just multiplying X by the element in the group A. Since A is a square matrix, the domain and codomain are both in the space, right? The input space. And it's a linear transformation such that this is an extra requirement for linear transformations. As we said before, it has to satisfy these two requirements here. Since A is invertible, then this transformation is bijective. So any subgroup of the general linear group is called a linear group. Let me give you an example. For instance, if you have this matrix here, you can make a the generalized linear group for this for two-dimension R matrices in R needs to satisfy this constraint here. Okay, so any A, B, C, D that satisfy this are part of this group. But for higher dimensions, it's not as simple, right? You have to define a notion of invertible.
So X we're speaking about would be this vectorized image.
Yes, the X here would be like 2 pixels. Yeah. Great question. I was hoping someone would ask a question. Excellent, very good. Yes, so there will be a two-dimensional vector here. And then the transformation will be, so for instance, consider this, a matrix here. What does this matrix do?
What is the element?
It's permuting, right?
Yeah.
Permuting 1 and 2. See, it's permuting them. So the permutation matrices are in the generalized linear group. Is a linear group. Okay, so now let's look at images. Let's consider a vector input. Remember, we are no longer talking about the tensors, right? We are talking about vector now. And then we are going to consider the general linear group with the dimension of the input, okay? Any matrix in this group will have to be invertible. It's an invertible 3m squared by 3m squared matrix that acts on the vectorized image via the matrix vector product. AX, right, where A is in this group. So the 90-degree rotation of our image is a linear transformation. We get vectorized the input, we apply this matrix, and we get a new vector, and if we unvectorize it, we get the rotated image. This 90-degree, this matrix here is invertible. And you can see that this matrix is quite large, right? It's a large matrix. Okay, so that said, question. If everybody is understanding what I'm saying so far, and it all seems very simple, I have an interesting question. Is there a transformation? Is the transformation of rotating an image 45 degrees in this group? No. Why not? You would think, right? 45 is fine because it was 90, you can do that. But does it satisfy the other properties that required in this linear group? I'm not saying that you're wrong.
I mean, I'm just kind of thinking that an event to the square and could rotate 45 degrees at the time, and it's not like that. That's how I'm thinking. You have texturized, right? That's
Right, exactly. So the question really is, what does it mean to rotate 45 degrees? I will show you an example. Let's get this cute dog and rotate the dog 45 degrees. Question. Can I invert this?
no.
No,
But you think
it's not a group. It's not part of the group. You cannot form a group with this rotation. Okay? Oh, I have a great idea. What about if I scale? I can scale, right? I don't need to prop the cute dog. I can scale it down and rotate it. Is that okay? Does that form a
that's
group?
fine.
It's fine. We have one fine. Is everybody fine? Yes, maybe? Yeah, all right. By the way, there was a paper that was wrong because of this. So think about this. Remember, in a group, I can compose, and the transformations must be in the group, right? And you must have an inverse. So if I apply a scaling up, I get this. This is not invertible. If I apply scaling down, I can write it so that what we are thinking is, oh, I could scale down and then scale up again. But the problem is the scale up transformation is in the group, so you can apply it directly to the image. And the scale and rotation, now you cannot invert this. So for this type of input, the scaling can't be done. Now, if you are in a point cloud, the scaling is fine. But in square images, the scaling is not okay. Which makes it difficult to deal with, right? And that's one of the reasons why CNNs have difficulties learning how to scale. Learning how to scale invariant representation. Okay, so let's look at then G-invariant transformation. So there's our presentation here focus more on the work that we did, so it's described the way that we described. So G be a discrete transformation group, okay, and T is a group. T may be a group representation. So it's this set of transformations, right, from the group. Now we are going to look for a transformation T bar. A transformation T bar is G invariant if and only if for all elements of my group, right, for all the representations in my group, I have that if I apply the transformation over the input and then apply T bar, is the same as applying T bar first. By itself, not first, by itself, okay? I want to find a T bar transformation. I'm not saying it's a group transformation. I'm saying actually it cannot be a group transformation. Think about it. I'm just saying that I want some transformation T bar that has this property, okay? I'm looking for it. Now, since the above is true for all x, right? I didn't tell you what it has to be true for all x, therefore it needs to have this condition here. Okay, so if I apply this transformation and apply T bar, is the same as just applying T bar. It's invariant. So what you can do, you can use the Reynolds operator, which is a way of creating this T bar matrix. What is that for finite groups? It's really simple. If you think about a linear group, you get the matrices that represent your transformations. You just add them all and average them, right? You just average them all. And this average transformation has this property. Okay? And I'm going to prove it to you. But before I prove it to you, I'm going to show it to you that that's the case. So here I have our rotation, 90 degrees. We have 4 pixels here. Okay. So the transformations are 4 by 4. And these are rotation matrices for the image. Okay. And what I am going to show you now is, if this allows me, these are, I am showing you what the, if I have image X, I am applying the identity to the image X, right, as a vector. And this is my image, it's just one white pixel. And now I rotate 90 degrees with those matrices, and you can see the rotation 180 to 70. Okay, so these are the transformations.
So since the matrix is 4 by 4, doesn't the image have to be 2 by 2? Because when you vectorize it, it's like 4 by 2.
Yeah, sorry, yeah, you're right. Yeah, the image is 2 by 2, correct. Actually, it's right here. I apologize. Yes, the image is 2 by 2. The Reynolds operator is we get just of this matrix, we sum them and divide by 4. That's it. Let me show what it looks like. It's actually not very exciting for 2 by 2 images. So this. Oh no, I don't want to do that. Okay, let's do this. So this is the average. Not exciting, is it? For larger images is more interesting. This one is not too interesting, but I think you will agree. Let's multiply this T bar by the identity. Well, that is obvious. We get the same, right? T bar. What about if we multiply T bar by the 90-degree rotation? We get T bar. If we multiply by the 180 rotation, we get T bar back. And then the 270 rotation, we again get T bar. So it has a property we want, right? Therefore, I just proved it. No, is that right? I show you one example and I'm done with the proof. Okay, so consider the proof is as follows. It's actually, you can make it a little more complicated and prove for infinite groups, but I want to make it simple. As simple as I can. So consider an arbitrary transformation T dagger from the group, right? And I'm applying T bar to T dagger. Then what happens is that let's expand T bar. T bar is like this. And then I'm going to, you see, since this is in the group, and this is in the group, their composition is also in the group. I am going to call this new group. Okay, so every single element of the sum is in the group, but maybe it's a subset of the group. So I'm going to call this G dagger because maybe it's just a subset of the transformations in the group. Now what I'm going to show is that G dagger has the same size as G. And if they have the same size and it's a group, they must be the same group. And that's essentially it. The proof is quite simple, is that the groups are closed on the composition and they have inverses. So all these transformations are bijective mapping. So this thing will take it to a unique other element in G dagger. So every single transformation will take it to a unique element. And at some point you run out of new elements, you just have G back, okay? So that's kind of the idea of the proof. Okay, so now I want to explain, talk about subspaces. If you're familiar with subspaces, just bear with me. It's important to explain this part. W is a subspace of a vector space V. If it is contained, it's a subset of V, such that the zero element is in W. That's important. For all elements X, any element in W, then a scalar times this element is going to also be in W. Okay, so all the scalars are in W. And if you have two elements in W, then X and Y, then X plus Y must also be in W, and that's all it means to be a subspace. If you satisfy these three properties, it's a subspace of this vector space. Question, is this line a subspace of R2? It's a unidimensional, if you can think infinite line, right? It has dimension 1, it's a subset. Is it a subspace? No. Why not? The zero is not in this, right? It has to always pass through the origin. W is a subset of all vectors in this line. Is this a subspace? Yes. Right? What about this? Is this subset of R2 a subspace? Why not? Yeah, exactly. If you get any point here and you scale, it's outside the space, so it's not a subspace. Okay. What about this hyperplane? Right, we have this three-dimensional. We have a two-dimensional plane passing through the origin. Is this a subspace? Yes. Right. For any two vectors, for instance, if you get any two vectors, if you add them, you're going to get some point inside this plane. And also if you scale and passes through the origin, so yes. Okay, so now let's talk about the basis of a subspace. Given a vectors x1 to xn, the span S is a set of all linear combinations of these vectors. You see, this is just using the notion of subspace. You're kind of defining subspace by forcing it to be this way. As long as you have a combination of this, if you have a combination, of these lambdas that will give you a 0, right? And then you just forcibly combine them to force them to be a subspace. So that's what the span is a trick to make it a subspace. So the basis of a subspace is a set of vectors, D vectors, that such that the span, right, of B is the whole subspace U, and extra is that B are linearly independent. There is no value of lambdas such that this product here will be 0. So to get the 0, the lambdas need to be 0. Okay, except there are no non-trivial values of lambda such that it's true. I should add that.
So this might be a stupid question, but linearly it kind of means they're orthogonal.
Yeah, they would be orthogonal.
Linearly independent will not mean orthogonal.
Yeah, not orthonormal, just Just you cannot get. So if you get a subset of this, it's gonna give you a different subspace. Like you understand? Like if I remove this basis here, I make the subspace. It's gonna be smaller.
Yeah.
And I need to add this one. Okay, so what's a G-invariant representation? So our goal is to learn a neural, right, whose weights are in this subspace W. The bias can be anything, and the activation function is some endomorphism in R. And we want this property, right, that if I transform the object, say I rotate it, is the same as if I did not rotate it, right? The output of this inner product is the same no matter which transformation I apply to the input, okay? This means that the output of the neuron does not depend on the transformations. Now I'm going to talk about equivariance. Equivariance is a slightly different case where it requires that transforming the input is the same as transforming the output. Now, what does it mean to transform the output? You see that you get to decide, but you have to decide in some consistent manner. Let me give you a special case. Suppose that there is this function, f, and I'm saying that's G-equivariant. If and only if, for all transformations in the group, if I transform the input, okay, and this function here, you can see that applies from this space to the same space. This would be equivariant. If I apply t to x, it's the same as applying t to the result of f of x, okay? But this is not a general case, because the general case is actually more interesting. As you can see, my function now maps m dimensions to d dimension. They think of the image embeddings, right? Embedding of the image. Now the definition of G-equivariance has to come through this notion of representations. If I have an element of my group, I say I want to do 90-degree rotations, then there will be a notion of 90-degree rotations of images, right? That we saw the matrices. It will be one of those matrices. And then I apply the function f, now I need to define a representation for the same notion of rotation in the embeddings. And as long as it follows the three axioms for what a representation is, you are good. It doesn't matter how you do it. You're gonna get some notion of rotation on the embeddings, okay? That's all you need. Yes.
Like, row 1 and row 2, they map from the same dimensional vector space, like M to M.
Yes, exactly, yeah. So this will be D by D, this will be M by M.
But G has 1, like they both.
G is an element in the group. For instance, the group is just an abstract notion of 90-degree rotation.
Right.
It's just an element that defines what 90-degree rotation is, and the group has. Sorry?
But on a matrix.
It's not no, it's just some abstract notion of 90-degree rotation. And then this row is translating that abstract notion into a matrix that rotates the object. You see? And this row 1, right? And this row 2 is translates that notion into a notion that rotates an embedding. Okay? That's all you need. They are invertible. So there is in the beginning I gave a properties for this representation. So there are properties that you need to have this. As long as you fulfill the properties, you can have any crazy idea how to translate this, and they're all gonna work. Okay. All right. So we are going to first focus on G-invariant representations. This looks way more complex, but I'm going to show you later that this is trivial. Doing equivariances, if you know how to do invariances, doing equivariances is trivial. Okay, so let's first understand the invariant subspaces. So a subspace M in RD is an invariant subspace of a linear transformation T bar if for any W matrix in this M, W T bar is also in M. Okay? Does that make sense? So if you think about the weights of your neural network, if they are in the invariant subspace, then if you multiply this by T bar, it's also in the invariant subspace. Okay? Let's make it simple. I'll give you an example of such subspace. The left one eigenspace of T bar is such a space because it's defined like this. W T bar is W. Satisfies this, right? I'm always getting W when I multiply by T bar. So there's only, right? So any element in this subspace here is part of the subspace by definition, because that's how I'm defining it. Okay, so all elements in this left one eigenvector, eigenspace of T bar is oh no, I have a question. Oh no, I didn't have a question. So for an eigenvalue lambda, the lambda left eigenspace of a subspace of Rn is it a subspace of Rn? Yes, right, because it has the zero element because this property is guaranteed if this is all zeros. If this vector is 0, then this is true, right? If I get two vectors on this subspace, you can see that if I apply u plus v, right, to T bar is u T bar plus v T bar. This is u plus v, which is an element of my subspace, right? Okay. I'm saying here, and if I scale, right? If I scale any element of the subspace, I get back an element of the subspace, because the subspace, you should be able to scale the vector. Okay? So what is the basis of this lambda left eigenspace of T bar? Is the set of all linearly independent left eigenvectors corresponding to eigenvalue lambda. As you can see in the equation here, right, is the definition of the eigenvector. what eigenvector for lambda equals 1, right? So that's why we call the left one eigenspace. Okay, so let's now show that the Reynolds operator satisfies this type of equality, okay? Because we need to show that this T bar can be the Reynolds operator. So the Reynolds operator is a projection operator, because if you do T bar square, you get T back. And you can prove this quite easily. You just expand it, right? And then you can show that T square applying twice is the same as applying it once. So it's a projection. And if V is not 0, all the left eigenvectors of T bar, the Reynolds operator, with eigenvalue lambda, this is true, right? And you can see, because it's a projection, the lambda has to either be 0 or 1, because if I apply it multiple times, I'm getting T back. So the eigenvalues, if you are doing the powers, can only be 0 or 1, right? To be stable like that. Does that make sense? Yes. Okay, so you see, like V T bar T square is the same as V T bar, which is lambda V, right? Therefore, this thing would be lambda square equals lambda. Lambda square equals lambda, then it has to be either 0 or 1 to be true. Well, could be a -1, but then lambda cubed, it would not, you have to be either 0 or 1. Okay, so since this T is invertible, right? We would have n non-negative. If we were to look at the eigenvectors of just the transformation rather than their average, it's a full matrix, right? You would have n non-zero eigenvalues and n eigenvectors. But the average may not be full rank anymore. The average may live in lower dimensional space, okay? And then can have 0 eigenvalues. We're going to get rid of those. Okay, so the left eigenspace of this T bar, our Reynolds operator matrix, with eigenvalue 1 is given by this. So this basis comprise a linear independent eigenvectors corresponding to eigenvalue 1 of T bar. And the span of this eigenvectors will be essentially this eigenspace. So therefore, any neuron weight in this subspace can be expressed as a linear combination of their eigenvectors with some alphas. Guess what alphas are in your neural network? You can choose whatever you want for alphas, right? These are the parameters. Interestingly, now, since T bar may not be full rank, do you have more parameters in the G-invariant neural network, or possibly fewer? Fewer, because you have, right? So if you had an n-dimensional input, would have n parameters plus the bias. But now you have the number of parameters of eigenvectors of T bar, which can be less than n. So this neural network actually has fewer parameters. This has been proposed by the Stu papers in 2018, which was so if we are saying that W is the eigenspace, right? Then, as we saw before, because the projection we get this, right? So that we are just using the eigenvector of T bar. But now we consider a neuron weight W and a set of 3 parameters alpha. And now let's consider the transformed input, right? We get X, we say rotate it, we get X prime. We have an activation function, sigma. And now if this W is constrained by this, is formed by these parameters, right? Weighting the eigenvectors, this is invariant to a transformation because it lives in the subspace, right? In the invariant subspace of T bar. So for any transformed input, you get that this is true. The transformed input inner product with W is the same as the untransformed input. So the output of the neuron is the same for your transformed images or not, or transformed object. And the proof is quite simple, right? It uses everything we have used. Essentially, the idea is that since this eigenvectors weighted by W form the subspace, this is essentially W, right? Our W T bar. Okay, so W is the same as W T bar, as we saw before. So, and T bar, when you apply the transformation T bar T is T bar, which is back to W. So it doesn't matter what you do, say when you transform, because this thing guarantees this, and this thing as the eigenvector is this. So you're done. It's the same output. Okay, so let's look at an example. In terms of complexity, it's has fewer parameters, but you need to do the weights of your neural network are this. We'll have to go through k inner products because you're multiplying the eigenvectors by the input. So or you're summing them. So it's a little more, tiny bit more expensive, but GPUs can do this parallel computation very efficiently. So it really, you won't feel it. So let's go through an example. Let's look at the MNIST image, and let's look at the rotation group of 90-degree rotations. There will also be a graph task later. So one thing that I want to say is these are 28 by 28 pixel images. We are not gonna, I don't want to build the rotation matrices. I don't want to do it, it's annoying. I don't want to do it by hand. So what I am going to do, I am going to use a black box, get NumPy rotate. And I want to identify what is the linear transformation that NumPy rotate is doing to the matrix. So any black box linear transformation, you can do this. It's very simple. Essentially is that if I gave you a basis of your space, or I can say a one-hot encoded vector, you would be selecting a row, you would be selecting a column of this transformation, right? So I give, instead of giving an image, I give this one-hot encodings for all the dimensions of my vector, and then I get back the transformation that whatever this thing is doing is implying. And that's it, that's all I do. It's very trivial to do, and you can do that with any black box transformation. So you don't have to go through the exercise of actually trying to think what is the transformation that I need. Okay, so we're going to use NumPy rotate to get this matrix. And let me show you the code. I'm just asking NumPy rotate to do the rotation here. And I'm giving an image as input, and this will be the one-hot encoded vectors. So I can get the actual matrix. Does it work? Okay. And now I am going to get I'm going to get the transformation from, I'm going to get the T bar, okay, from the image. I'm applying T bar, right, the Reynolds operator to the image. When I do that, I get this, okay? Can you see the symmetries there from rotation? If I rotate, right, it creates this symmetric version of the 4. So let's look at the code for this. I want to show you an example with this code. So now I went through the exercise of trying to know what the linear transformation T bar is from the NumPy rotation. And here I'm applying them and average them. And here I got my linear transformation, my average, and I'm applying it. So essentially it shows that I got the right transformation from the black box. Now let's look at, so since the Reynolds operator is the average over all these transformations, let's look at G as a permutation group. Let's see what what our subspace looks like for the rotation, for the permutation group. So this is the T bar, which is difficult to see. But I'm going to show you how it acts, like how it gives me the right neurons, okay? So let's look at the eigenspaces now. So let's look at the rotation group. So what I'm going to do here, I am going to ask for the eigenvectors of the Reynolds operator matrix, okay? And this will give me the basis. And this basis is where my neurons are going to live in. And we also give me the eigenvalues because I need the ones that are 1 rather than the 0 ones. Okay. Also, I want to find the rank of this matrix because I want to know which ones are non-zero. I don't want to be looking at tolerances because they are never 0, they are close to 0. So I want something simple to tell me what's the size of my subspace, right? How many bases I have. And then I'm going to display it, and then I'm going to show some of this. I'm going to save this eigenvector, okay? So let me do that. And let's visualize these eigenvectors. Let's see what they look like as images. So these are the bases. Oh. So these are the bases. These are the eigenvectors of the Reynolds operator. Okay, this will be the basis for my invariant neurons. Can you see an interesting property of this thing? They're all symmetric. You see, think about multiplying this thing by a scalar alpha. Whatever value that you get here, you get here, you get here, and you get here. So if your number is rotated, the same places will be multiplied by the same parameters, right? And these are all the bases for this 20 by 28. I can say there are quite, actually not all the bases. There are 196, I think. I'm just showing 8 of them. Okay, so the eigenvectors of the Reynolds operator, then my neural weight is going to be these scalars, right? My parameters times each of these bases. There are 196 bases. I have 196 parameters for this. Let's visualize a random W. So we're gonna pick a random W and we are going to vectorize it. So here is what I was showing earlier. This is one of the eigenvectors, and I'm multiplying this eigenvector by the 90-degree rotation. You see it? It doesn't change. It's the same. Okay, so any of these elements, any of the parameters, right, in this invariant subspace will have this property. Any of the parameters will have this property, right? So let's see for the permutation group of graphs. And I can guarantee you that you'll be disappointed by this one. So I am looking for the Reynolds operator of the permutation over graph, okay? I want to learn get a graph as a vector and then learn an output from a neural that is invariant to permutations of the adjacency matrix, okay? The T bar looks like this. The rank of T bar, these are the eigenvalues, okay? And the rank of this T bar of a graph of size 25 by 25 is 2. What do they look like? What do the eigenvectors look like? This. What is it? To make the linear invariant neuron or a graph, you can only have one parameter for the diagonal and another parameter for all the rest. If you wanted to make it invariant. And here comes the realization that we don't build graph neural networks that are invariant for each layer because of it. We build them to be equivariant. Equivariant, then we have more accepted problems. So we don't do one layer invariant, because this is what you get. Okay? Now let's construct this G-invariant neuron. Let's look at the parameter in the subspace. Now we know how to do it, right? We have this 196 parameters for our eigenvectors. And let me show you this interesting thing. So this is a random parameter that I got from my subspace, and I'm doing the inner product with 4. I get this output for my neuron. Okay, before the softmax or before the activation. If I rotate, same value. We just constructed an invariant neural network for rotation. You can just plug this in PyTorch and it works perfectly. As actually, when I was teaching this, at the time the iPhones could not identify people upside down. And I would tell my students to please contact Apple and send the lecture, because it's very easy to build CNNs that are rotation invariant. Of course, when you have not 90 degrees, but it's quite robust. Okay, so now for the permutation group, there are only 2 bases, and it's a lot less interesting. Because if I have some matrix here for my graph and I permute it, I get the same value, but you can see that these are just 2 parameters. It's not that exciting. Okay, now how do we then? So now that we know how to build one invariant neuron, let's build an entire neural network from it. So what I'm going to do is the first layer, I'm going to stack it with invariant neurons, G-invariant neurons, and then the rest of the neurons can be regular neurons. Question: can I reverse this? Can I first do the standard neurons, then the G-invariant neurons? Right, because you see, once this applies to your transformation, now you have these transformations that are not in your group anymore. You don't know anything about them. So this thing is not going to work, right? So the invariances are defined in the first layer. Okay? But once this is invariant to the transformation, they all invariant to the transformation. After this, you don't care. You can do whatever you want. So the change is really in the first layer. Okay. So let's do some experiments from MNIST. I know it's not super exciting, but it's what my laptop can run. And actually, my laptop is so slow that we're gonna take questions after I start running, because I'm actually gonna learn this. So this is my training data, okay? Training data. In the standard way, this would be my validation data. So I'm selecting hyperparameters from this validation data. And then I'm going to call this my in-domain data. It's sample from the distribution of the handwritten digits that I saw in training, right? They are all upright. And this is my auto distribution test data, which are all rotated. Okay, so let's go and do this. Now first start with the standard MLP, right? MLP with MNIST, it works. I don't know if you tried, it works pretty well. MNIST is such an easy task. Okay, so let's look at simple neurons, right? We have this ReLU activations, very simple. First layer, second layer, right? So the first layer is a linear activation, then another linear, and finally the softmax, right? So it's just one hidden layer neural network, quite simple. Okay, so now let's, do I have to skip anything? Okay, let's train this thing. Did it work? Yes. I'm open for questions, Because this is all happening in real time. My laptop is an Apple, so it's slow. Yeah.
What is the level of
For the symmetry. Yeah, so for the symmetry group, right? It's just, what is the element of the symmetry group? If you have, say, 4 elements, it will be just a vector saying like 1, 3, 2, 4, which means 2 and 3 have been permuted. So that by itself speaks nothing. You don't know what to do with it. So what you do is then build the representation of this element of the group, which is how you're going to permute things on your space, right? And now if I give you, say, a point cloud, n by 4 by 3, right? 3 dimensions and 4 points. It's going to tell you how this matrix is vectorize the whole thing. And this matrix is going to tell you how to compute the columns of this thing. So the new vector that you're going to get is a vectorized version of a permuted point cloud.
So the levels of which we find so say yes, so
Yeah, so in this case, it would be, so each transformation is a, 12 dimensional, 12 by 12, right, matrix, and then you average all the permutations. So you look at all the permutations and average them. And that is the Reynolds operator for the permutation group. Yes?
A little bit more involved question. So you have different kinds of symmetry, rotational symmetry, permutation symmetry. And then you're building a representation of that, which is essentially a matrix, right?
Right.
Can you always do that for all kinds of symmetry?
No. So the linear group is, as you imagine, restricted, right? It doesn't capture all possible symmetries that you want to have. But interestingly, if you look at all papers, it's always linear. I'm going to show at the end how to do nonlinear. For nonlinear, it's significantly more complex.
Can you give me an example of a symmetry where you cannot do that? I'm very curious, like when you cannot.
Conformation of molecules, like molecular conformation. There are symmetries there that are like, they're not linear. So it's harder.
Like since the starting of the tutorial, I've been thinking this seems too simple. Like, can you always do that? Okay, you cannot always do that.
You cannot always do that, but as I'll show at the end, there are tricks that we use to deal with those cases.
So this is the one that I'm basically Reynolds operator, right? That is the time variance.
Right, yeah, it's in time variance. What is going on? Oh, I know, maybe this Zoom is taking a lot of processing time. I have more time for questions. This is the problem with doing this
How
live.
many parts do we need?
9. So it's.
Other question.
More questions.
Yes.
Are we learning about the G-invariant neuron prerequisite for graph learning?
Yes, that's what the theory of graph and stat learning is about. But we'll see that for those, like we use other tricks also. But I'm just giving you a general recipe for building G-invariant, G-equivariant networks. So whatever transformation group that you are interested in, as long as it can be mapped into the linear group in this case, you can do this. And it's quite easy. It's like just finding the left thing.
That's really cool.
Yeah.
I have a question.
This is, yeah.
Correct to do that. This is like super powerful only for finite group. Like if like for rotation we had like 4
Yeah.
90 degrees, but like every rotation.
Yeah, we are going to. So the second part of the tutorial will be on Lie groups, which are arbitrary rotations on this 3D space or 4D space, 3D space. And for those, the idea is the same, but the math is different. because we have to use the algebra, we cannot use the, how you're gonna average overall, you cannot do that. But once you do the exponential mapping of the Lie algebras, it's pretty easy to find the ranges. I thought my computer was faster. No, it's an M1, it's not bad.
Oh, it's so.
You see, that's the problem of not having GPUs. I bought a PC, but I hated Windows so much for my course, right? That I prefer to wait. Also gives, any further questions?
Maybe people who have questions.
Oh, they can, I cannot, I don't wanna touch it.
Tell us what's going to be the topic of the next part of the.
Right, so, the next part will be, Lie groups, like how to deal with continuous transformation. And then I'll talk about, the case where, what do we do when we have nonlinear, we want nonlinear transformation, that's the next part. And then, also we start with set representation. So how to represent set, and I'm going to start with the transformer. So the first part of the set lecture is the transformer, just to make it more exciting. And then I'll talk about generally how we do set representation. The transformer is just one way of doing set representations if you remove the positional equalities. I don't think I needed to go this, I know I'm going to reduce them. Oh, I can change it. Oh, I was smart, I gave a parameter. The next one will not be this long, I promise you. You're almost there. We are watching paint dry, I did not think this through. Okay, so I think we are done now, I hope so. Okay, so, let's plot the confusion matrix here. If it is done. Training. Oh, it's not done training. They magically appear here. So of course, right, what we expect is that the MLP is going to do pretty well in domain, right? But then our distribution is going to be a pretty bad predictor. Come on. It's a good time to get questions, but I think we are running out of them. No, it's already, it should be in the queue, right? For the. Because the reason why I do that for my course is that I want the student to really know that I tried. I really try to learn, but it doesn't quite do that. Oh, there is someone talking. Oh, that's me. Oh man, what's going on in this thing? I don't know. My laptop is not that slow. It is not. It must be the owl with the Zoom that's messing it up. Okay, so let me talk about the experiment for the G-invariant then. Our G-invariant is going to be exactly the way that I'm showing here. Is it exact neural network with the G-invariant neurons first? And we save the basis of the eigenvectors, and then we load them, and this is quite simple. See, with the basis, I have this basis, and then what I do is for the coefficients, I have this parameter. The parameters have the same size, right? Same number of parameters as the basis. And here I'm just initializing these coefficients, the alphas. So in the forward, what I'm going to do is I am going to put the basis in the GPU if I have one. And then I multiply the coefficients by the basis and I get the weights. And now these weights, you can use exactly the way that you would use weights of a neural network, right? And you multiply the weights by the input, you get this inner product, you add a bias, and this is your new linear layer. And this exact linear layer here, you can just replace with the original linear layer with this. And if you do that, your GNN is gonna be a G-invariant. Right, and then see, like in my MLP, I'm just replacing the first layer with the G-invariant layer, and the rest are just the regular ones. And then we are going to train for 2 epochs later. Okay, so let me go back. Hope it's done. Oh yes. Okay, so this is the confusion matrix, right? There are 10 classes for the MNIST. This is the train accuracy in domain test, 94%, highly accurate. This is the accuracy when you rotate. Pretty bad, right? And now we are going to go through this, and do not worry, 2 epochs. There are fewer parameters also, but we have all this. We have to add all the bases, so that
It's just a linear combination, right?
it's just a linear combination. If I had a GPU, we would be having lunch now. But yeah. And Apple did the tragic mistake. I used like when Apple had compatibility, I used to carry the GPU with me so I could use the Mac. But now they think that they are better than NVIDIA, and it doesn't work anymore. So okay, well we'll go back to this. Now I have a few extensions, right? So what if you want invariance to multiple groups, right? You have this rotation group, you have flips, you have a bunch of other things, and you have permutations, you have many things you want to be invariant to. What do? The solution, one solution is, well, you just form the group with all the permutations, possible permutations of these operations applied, right? And that new group, that's the group that you need to be invariant to, and you do the same thing with Reynolds operator for this group. Yes.
Does the order matter?
It might matter, and that's why they are doing this way. If these groups commute, then it's much simpler, because it's essentially the product of the Reynolds operator for each group. And that is pretty easy, right? So if they don't commute, you gotta make sure that you have all the operations inside your group, right? If they do commute, then you just do the Reynolds operator and then make the product of all of them, and you should be fine. Okay, so that's one. And then there is another thing that for instance, we have done is like I have all these groups, and I do not know which groups I need to be invariant to for my data. For instance, for MNIST rotation, in your training data, you're going to see that 6 and 9 are things that you can't really tell them apart. So if you want to kind of choose which groups are the correct groups for your training data, we have a procedure to do that. You'll learn which groups are the right groups for your training data to be invariant to. Because if you can be invariant to something, why shouldn't you? For instance, if you're training on ImageNet, if you could be invariant to rotations, why wouldn't you be invariant to rotation? Right? If it shows that the images don't care if you're invariant to rotation, then you should be, right? Invariant to flips, invariant to horizontal, vertical flips. So that's that part. Okay, let me continue, equivariance.
Good question.
Yes,
Does the size of the group make the problem more harder or less, or like if it's harder than function effectively?
good question. If you are just adding it, when you say harder, you mean harder computation?
More data to train.
Oh, more data, no, so it depends a lot on the rank of the Reynolds operator. Because, for instance, for permutations, we saw 2. That is pretty easy to learn, but also it's going to perform very poorly. By the way, for equivariances, there are 15, so it's not like you have way more for equivariances, but at least it's not 2.
Variance combined with like data augmentation, right? Like we're like close to like it for data.
Right. So when you do data augmentation, what you are telling the neural network is, look, I want you to learn to be invariant to this transformation. So what will happen is actually quite interesting. So if you have data in your domain in test, right? You have certain like eminence data, then it will learn to be invariant to transformation of things that look like eminence. But if you then give it a cow, it's not going to be invariant to that because it's never seen it. It doesn't know how to be invariant to it. Yeah. That's the issue.
You have one parameter redundant.
Right.
You don't need full rank linear algebra to learn things that are invariant. So, like you only need the basis for your Raynaud.
Right. Yeah.
That's all you need.
That's all you need. Yeah. But I think the question was, what if I forget all this, I get MLP, and I just rotate my eminence during training, and give it as training data, like for the data augmentation.
Yeah, I guess you can do that, but like
It doesn't guarantee you that, right?
it depends on if you actually converge, like
Yeah, so here's the interesting thing, like, even if you converge, and even if that means that your embedding is invariant, which is not, because the softmax essentially is just a hyperplane. So you're gonna be the hyperplane of the softmax, but maybe the embeddings are different. But suppose that you converge to the same point, is all beautiful. Well, you see, you only told your neural network to be invariant to rotation on that domain. If you change the domain and you try to do transfer learning, it's gonna be terrible because it doesn't know how to do that outside the domain. So for transfer learning, it's bad. So for transfer learning, you want something that's actually either invariant or equivariant. Yes.
This is sort of like every performance. So if you, for example, you have one of this variant space, right? And maybe also have some
Right. Yes, that is true. For instance, when you do geometric modeling of molecules, right, you want the generator, not to pay attention to the specific rotation in space or conformation, right? You want it to be invariant to those things because it doesn't matter. It would generate the same molecule. So for generators, but then there is one small funny thing, is that we don't know how to do that too well. So the actual generators, what they do is that they will assume a conformation, like assume a specific orientation, and then try to for instance, diffusion method, they try to do diffusion on that specific permutation or conformation. So it's sensitive in that way. But the problem is that then you need a lot more data because you need to learn how to get this thing from this specific orientation and generate a new thing, right? And if you change the orientation, now you have to do the same thing, but it's like learning again, because for the method it's going to be different. So ideally, your neural network should not be sensitive because then you don't need that much data to generate, right?
why
It's just because in a lot of cases, it's just really difficult to capture all the information in the invariant model. It's not very clear, to be honest. I know, for instance, for earlier work on using LSTM to do molecule generation, I know exactly why. And one of the reasons is that you really need to capture distant complex correlations in your data. And this kind of positional dependent representations are easier to talk about distant correlation. When you make it equivariant or invariant, it's much harder to talk about distances, long range correlation. That I think one of the main challenges, but I believe it's solvable. It's just that we don't really know how to do that right now. Okay, I think we are done here, I hope, not yet. So let's talk about equivariances. G-equivariant neurons we are going to do this, right? Our property that we want is such that if I multiply, I get my parameters. Now my parameters, I'm not just looking at one neuron, I'm looking at a set of neurons, right? One neuron equivariance makes no sense. So I have a set of neurons, so instead of a vector, I have a matrix here, okay? And I'm going to get a set of neurons output. So if I rotate or I apply the transformation on these neurons, is the same as applying the transformation on the input. Okay, so I need this constraint here. This thing here is something you have to design yourself. You have to decide what this means, right? And this generally comes from the problem. Okay, so now let's, since this is true, right? Since this is true for all x, again, we have this equality, okay? And since this has an inverse, right? I am going to apply the inverse on this side and get it here. All right, so I have this. Now, the real trick, what does this look like, is that I always want to do the transformation parameters, transformation input. And this is not that form, right? But how can I then get this to the other side? Again, I get this parameter matrix, and I'm going to vectorize it. I'm going to make it a vector. And once I make it a vector, I can use a Kronecker product to define this equality as a vector matrix vector product. Okay, so this is the Kronecker product between this and the inverse. This thing here is going to be, if these are linear, this is linear. It's a G-invariant on a larger space. Okay, now you know how to do G-equivariant network, because that's it. And then the same toolkit that we showed applies, right? Reynolds operator, the whole thing. So let me show you an example. Well, this is just showing the Kronecker product. If you're not familiar, Kronecker A and B is all the elements of A multiplied by the matrices B. So it looks something like this, right? So then it's the same idea, right? This is your transformation now. It has inverses. We can show that this forms a group. Okay, it has inverse. It has an identity. It distributes and yeah. So that's exactly what we need. And now our transformations are this, and you can prove that it has the same property. The Reynolds operator of this group has the same property as the ones we saw in the G-invariant neural network. And that's it. The equivariances and invariances are not different. They're just the same thing in different spaces. Okay? And just to finish up. Oh. Okay. Hopefully I don't have Apple stock, so it's good. I'll just leave it here. We are not going to wait until this. Well, you believe me when I say that the tests, both cases will be exactly the same because it's G-invariant, so it's all good. Any further questions? So when we, I have, when does, Babak, when is the, what time is the next,
We have two.
two? Yeah, so, I think it's okay if we stop now, right? Okay, so at two, I'm going to talk about Lie groups. And then I'll talk about specific tricks that we do for set representations, okay? Today, and then tomorrow, I am going to talk about graphs, graph representations. And for graph representations, I'm going to explain the connection between graph neural networks and eigenvectors, which is something that's very strange, that I hope we all appreciate the strangeness of the whole thing. And then I'm going to explain like what GNNs can do, what they cannot do, what eigenvectors can do, what they cannot do, and how to make them better, like both of them. And also going to explain how to fix new GNNs to do tasks that that they can't intrinsically do the way that they are, right? We have to do something in them to make them do these other tasks. And we talk a bit about hypergraphs. Okay?
Awesome.
Okay, excellent, thank you.